Greetings! Today we will be talking about functions. Now, I'd have to say that the concept of a function is probably one of the two most important concepts that form the bridge between pre-calculus mathematics and calculus, the other being limits, which we'll discuss later in the chapter. Now, a function, so here's the definition. So a function is a rule that assigns a unique number, and pay attention to this word unique, we'll talk about it later on, that assigns a unique number. This number is called the output to every element of a specified set. And that specified set is called the domain. So a function is basically a rule that gives you one single unique output for every input that comes along. And these inputs come from a predetermined set that is known as the domain. So to specify a function, you need two things. You need the rule and the domain. Okay, so if the domain is not specified, then it is usually taken to be as large as possible. So whenever the domain is not specified, it is taken to be as large as possible. And this rule of thumb really becomes important when you have actual equations. So if you have an equation that defines your function, the largest possible set on which that equation can be defined will be the domain, unless a domain, a smaller, more restrictive domain, is specified. So functions can be described four primary different ways. So there are four main ways to describe a function. So the first one is a table. So you can have a table of data, and the table will have a column of inputs and a column of outputs. So you can literally define the outputs based on the inputs from the table. Another way is with a graph. So a graph can also be used to describe a function. The third way is with an equation. So sometimes functions are described with equations. This is probably the way that you're most familiar with. And finally, an equation or a function may be described with words. So each of these are legitimate ways of describing a function. And sometimes you can describe a particular function more than one way, and those ways are not mutually exclusive with one another. So for example, an equation that can be, or a function that can be described with an equation can often be graphed. But the converse isn't necessarily true. You can have some wild graph. So for example, say here's y, and here's x, and I have something like this. So every x value, so the x values would be the inputs. And to find the output, so let's say this is 5. So to define the output, we just look at the y value. And maybe this y value is, let's say, 6. So if 5 is the input, so 5 is some element on the domain, the output of the function would be the number 6. So in a similar way, any element from the domain can be put into the function, and you can see what the output is just by looking at this graph. So typically, the domain or the inputs are down here on the horizontal axis, and then the outputs are on the vertical axis. So the output is y and the input is x. So let's see a few simple examples. So some examples. So the first one It's a little bit of a unique example in that the domain does not involve actual numbers. So I want you to imagine your classroom. So here's your classroom, and you have people in the classroom. So here's one person, here's another person, another person. So you have a number of classmates, like that. Now, the classmates, so the students, will consist of the domain. So the domain will just be the group of students. So I'll put some curly brackets. It's the set of students will be considered as the domain. And what the function is, so the function basically outputs the age of the given student. So there's a rule that assigns a unique number to every element of the domain. So every element in the domain, which is simply the classroom, it's the students in the classroom, is assigned a unique number. So for example, here we have John, and John is 23 years old. And this is Sally, and Sally is 19. And here's Henry, Henry's 22. And here's Max, Max is also 22. And here's somebody else who's 20, and then here's another person who's 23. So the function would return the age of the person. Now notice that the function associates only one age to each person. Right? So I forget their names, but this person and this person both have the same age. That's okay as long as every single person that walks in, there's only one single number assigned to that person. So it's okay if you assign the same number to more than one people. More than one person can have the same age in your classroom. But every person only has one number assigned to him or her. And that is exactly what it means, a unique output. Every input only has one output associated with it. Now you can assign that output to multiple inputs, but the whole point is that each input uniquely specifies an output. So you can always think about this classroom example to avoid confusion, right? The people in the class, the students, are the inputs, and every student has a unique age. You know, John isn't going to be 23 and 45 at the same time. He's either 23 or he's 45. So that's what it means, a unique output. And it does not preclude two individuals from having the same output. Two people can be the same age. It's just that every person has only one age. Right? So the second example, I'll list these down here, would be population as a function of time. So I've got a chart, so let's see an example of a table. So this is population in Vancouver as a function of the year. So each year has associated with it a unique population. So in 1911, the population of Vancouver was 100,401. We'll just assume that these are all on January 1st of the year at midnight. So the population can constantly be shifting. But for every moment in time, there is a unique population for any given city. In 1981, the population was 414,281. Notice that it may be difficult to describe these data with an actual equation. You might be able to model it with an equation, but there's not a given equation. So we want to understand how to work not only with equations, but other formats in which functions may be given to us, such as a table, such as this. The third example of a function that we'll talk about will be the tides. So we'll think of water level as a function of time. So again, we have something that's a function of time. So every time, the time would be the input, 12 o'clock, 9:25 a.m. And then the output will be just the water level in a given harbor. So let's look at, in this example, we have a graph. So this is in Alameda, and we have, so there's actually a prediction, which is the blue curve, so that's a function. And we have a bunch of observations. So you can ignore the observations, but you can see that mathematics is pretty powerful just by looking at this graph. This is kind of a weirdly shaped or an oddly shaped curve, and yet it's very, very close to describing the actual water levels. It might be a little bit more complicated than a basic sine or cosine, but that's pretty cool that it matches so closely. But what we should gather here is just that we have the time on the horizontal axis, and then the vertical axis tells the sea level, right? So it's basically feet above some, average value or basic, sea level. So, the sea level at a given moment might be 6 feet above the average, and then it decreases to here's low tide, high tide, low tide, high tide, and so forth. You can see some high tides are lower than others and vice versa. But each time there's a unique water level, right? The water level is a unique number that is determined at every moment in time. So if you tell me what time to look at, I'll tell you what the water level is. One number coming out. So this is an example of a function. The next example is a little bit different. Salinity. Now, salinity is basically a measure of salt concentration. So even though the units in the graph that I'm about to show you are a little bit different, you can think of this as grams per cubic centimeter. So for every amount of volume in the water, how much salt is dissolved in that water? So we're looking in the ocean, and we're looking at salinity as a function of depth. So based on how deep you are below the surface of the ocean, you might have a different salt concentration. And this is actually a function that can be described mathematically, and here is a graph of it. So here we see the salinity on the horizontal axis this time. So the standard roles are reversed. Normally you would put the domain on the horizontal axis. In this case, the domain is on the vertical axis, most probably because they wanted to visualize it with depth of 0. So this is the surface of the ocean, depth of 500 meters, 1,000 meters, 1,500 meters, 2,000 meters, and so forth. But for every given depth, you have a unique salt concentration, which you can read off of the horizontal axis. So at a depth of 500 meters, this would be your salt concentration, and so forth. Now, all of these examples show a single input. Sometimes a function can take on a multiple input. And the whole idea is that it's just some set as the domain. A set can be a set of pairs. So you can have 2 items coming into the function instead of just one. And you've already probably experienced one such function. If you're older than 21, you might have received something like this in the mail on your 21st birthday. So this is a blood alcohol content chart for males that tells the approximate blood alcohol percentage as a function of the number of drinks you've consumed and your body weight. So a male weighing 180 pounds who has had 4 drinks most likely has a blood alcohol content of approximately 0.08, and they are legally intoxicated. So you see that the amount of your blood alcohol content is a function of your gender, your body weight, and the number of drinks you've had. And there are probably other factors if you want to develop a more elaborate model as well, because everybody's a little bit different. But this is another very interesting example of a function that takes on more than one input. Now in Calculus 1 and 2, we focus exclusively on functions that have a single input. But later on in Calculus 3, we'll see more examples like this, where you have a function that is described with multiple inputs. And we'll be studying how the outputs vary as you vary one input or the other input. And as a final example, this example is very useful in physics. We can consider, so I'll call this 6, a particle moving on a one-dimensional line. So for example, if we have the x-axis like this, and we have some 0, 1, 2, 3, 4, 5, you can imagine a ruler sitting on a desktop, and a marble, so there's a little groove in the ruler, and put a marble on the ruler and let the marble roll back and forth along the ruler. So this is exactly one-dimensional particle motion. So in this case, the particle's position will be a function of time. So let's say the particle's position x will be a function of time t. So for every instant in time, the particle has a uniquely specified position. At 12 o'clock, the particle was at x is equal to 1. So in this case, x equals 1 is the output, 12 o'clock is the input. At 12:01, the particle was over here at x is equal to 4. At 12:02, the particle was moved back to x is equal to 3, and so forth. We'll be discussing this example of particle motion in a line in more detail in subsequent sections.